Hello students, I hope all of you are well and safe. Please take care of yourself. So in our subject applied thermodynamics, we started unit 6 in the class. If you remember, we discussed initially the classification of compressors and then different types of compressors and their working. Later we also discussed different performance parameters of compressors like different efficiencies, maybe isothermal efficiency, isentropic efficiency, polytropic efficiency, volumetric efficiency, free air delivered, etc. And thereafter we started the analysis part of reciprocating air compressors. So single stage reciprocating air compressors, we had seen the working, and then we derived equation for work done in single stage reciprocating air compressors. Thereafter we studied about multi-staging and intercooling. So multi-staging is nothing but compression of the fluid in number of stages, that is more than one cylinder, maybe 2 cylinders, 3 cylinders likewise. And intercooling means in between 2 cylinders we provide one heat exchanger called intercooler, whose function is to take some heat from the working fluid and cool the working fluid, so that temperature of the fluid is dropped, and in the next stage less work will be required to compress the fluid. So now let us move ahead in the analysis part. So we will start with two-stage reciprocating air compressor, the analysis. That means the equation for work done, different conditions, etc. So let us see. So let us see in this diagram. This is a PV representation of two-stage reciprocating air compressor. We can observe 0 to 1 is suction of air or fluid in cylinder 1. 1 to 2 is compression in first stage or first cylinder. Then 2 to 2 dash is intercooling. In intercooling we know some heat is rejected by the air in the intercooler. Hence the temperature will be dropped, volume will be reduced slightly, because it's a constant pressure process, constant pressure cooling. And then 2 dash to 3 dash, you can see, is the compression in second stage or second cylinder, and this is the final pressure at which the air will be discharged from the compressor, which is called as discharge pressure or delivery pressure, which is P3 in this case. Suction pressure is P1, and intermediate pressure means the pressure after first stage compression is P2. Now we will have to derive an equation for work done or work required to compress the air in two-stage reciprocating air compressor without clearance. That means clearance is not considered. You can see here clearance is not taken into consideration, and with perfect intercooling. Now we had shown the intercooling here, but what is perfect intercooling? I think we discussed earlier, but I will recall. Perfect intercooling is the one in which the temperature of the air or fluid after first stage compression is brought to the initial temperature at which the fluid enters into the particular cylinder. Like here, air is entering at temperature T1, it is compressed to temperature T2 in first stage, and then it is intercooled, so its temperature is dropped. Now if this temperature T2 dash is equal to initial temperature T1, then that intercooling will be called as perfect intercooling. So we need to write the work done required in this two-stage reciprocating air compressor. So let us try to derive this. So we can see already we had derived equation for single stage reciprocating air compressor, which is nothing but work done in any stage, single stage, is given by, if n is the index of compression, okay, this curve is following this equation, PV raised to n is constant, so n is the index of compression. So for that, work done is given by n upon n minus 1 into P1 V1, where P1 is the pressure at which air enters, V1 is the volume at which it enters, in bracket P2 by P1, discharge pressure upon suction pressure raised to n minus 1 upon n minus 1. This is the generalized the equation which we derived earlier for work done in single stage reciprocating air compressor. Yeah. Now we want to derive the equation for two stage reciprocating air compressor. So what we will have to do is, we will have to just add this work plus this work done in this, or work required in this stage plus work required here. Okay. So I can write work done in two stage reciprocating air compressor is given by work done in single stage, that is this stage. So it will be what, as per this equation, n upon n minus 1 into P1 V1 into bracket P2 by P1 raised to n minus 1 upon n minus 1. This is first stage, plus work required in second stage, again n upon n minus 1 into here entry to the second stage P2 dash V2 dash, okay, P2 dash V2 dash into bracket discharge final pressure from that stage P3 upon initial pressure in that stage, that is P2, P3 by P2 raised to n minus 1 upon n minus 1. So this is the work done in two stage reciprocating air compressor. Now here you can observe, as I said, if there is perfect intercooling, then what is the condition? The condition for perfect intercooling is the temperature T2 dash will be equal to temperature T1. Temperature after intercooler is equal to initial temperature in that stage. So with this, if we write the equation of state between the state 1 and this state 2 dash, okay, so for that I can write P1 V1 upon T1 equal to P2 V2 dash upon T2 dash. So as T2 dash is equal to T1, I can write P1 V1 equal to P2 V2 dash, P2 dash V2 dash. Okay. So now we can replace this here. Okay. So my equation becomes, now I can observe n upon n minus 1 is common. Now P1 V1, here again it is replaced by P1 V1. So this is common term. Okay. So I can take it as common, n upon n minus 1 into P1 V1 in bracket. Here it is P2 by P1 raised to n minus 1 upon n minus 1 plus P3 by P2 raised to n minus 1 upon n minus 1. So minus 1 becomes minus 2. Okay. So we can write work done will be equal to n upon n minus 1 into P1 V1 in bracket P2 by P1 raised to n minus 1 upon n plus P3 by P2 raised to n minus 1 upon n minus 2. This is the equation for work done in case of two-stage reciprocating air compressor with intercooling, with perfect intercooling. Now we will have to also think about the condition at which this work done or work required to compress the air will be minimum. That will be the work at which we will get the maximum efficiency. So let us try to derive the condition for maximum efficiency or minimum work required. So for this, what we will have to do is, we will have to derivate this equation with the variable and equate it to 0. Now we will have to decide the variable here. So here you can observe the index of compression n is constant, discharge pressure P3 is constant, intake pressure P1 is constant. So we are left with only one variable here, which is nothing but the pressure P2. Only variable. So you will have to find the condition at which efficiency will be maximum. The particular pressure P2 at which efficiency will be maximum. So for this, what we will have to do is, we will have to just derivate this equation with respect to P2 and equate it to 0 and find the condition. So let us try to achieve. So I'll say dW upon dP2, that I'll equal to 0. Okay. So let us see. Now this is multiplication. Okay. So it is constant already. So this is nothing but the derivative of this with respect to P2, that is P2 by P1 raised to n minus 1 upon n plus d by dP2 of P3 by P2 raised to n minus 1 upon n, and again 2 is constant, so that will be 0, and this must be equal to 0. Okay, so 0 is equal to, now here P1 is constant. Okay, so we can write separately 1 upon P1 raised to n minus 1 upon n into derivative of this d by dP2 P2 raised to n minus 1 upon n plus here P3 is constant, so P3 raised to n minus 1 upon n into d by dp2 of this 1 upon P2 raised to n minus 1 upon n. This will be equal to let us say 1 upon P1 as it is raised to n minus 1 upon n into this. So it is n minus 1 upon n into P2 raised to n minus 1 upon n minus 1 plus P3 raised to n minus 1 upon n into, now I'll take let us say d by dp2, this is, if I take it here in the numerator, okay, it will be 1 minus n upon n, okay, it's taken in the numerator. Okay. So it is 1 upon P1, let us say n minus 1 upon n into n minus 1 upon n into P2 raised to what? This is n minus 1 upon n minus 1. So n minus 1 minus n. So minus 1 by n. Minus 1 upon n plus P3 raised to n minus 1 upon n into this. So it is say 1 minus n upon n into P2 raised to 1 minus n upon n minus 1. So 1 minus n upon n minus 1. So can write here 1 minus n upon n minus 1. So it is 1 minus n minus n. So 1 minus 2n upon n. So it is 1 minus 2n upon n. This is equal to so let us say I have taken P1 here in the numerator, okay, or we can keep it as it is. So 1 upon P1 raised to, let us say, n minus 1 upon n into n minus 1 upon n, P2 raised to minus 1 upon n. This is 1 minus n upon n, so it can be n minus 1 upon n with negative sign. So that will be multiplied here, so it becomes negative, okay. In bracket I can write say n minus 1 upon n, okay, into P3 raised to n minus 1 upon n into P2 raised to 1 minus 2n upon n. So this term we can take on this side because it is 0 here, okay. So I can write now 1 upon P1 raised to n minus 1 upon n into n minus 1 upon n into P2 raised to minus 1 upon n equal to n minus 1 upon n into P3 raised to n minus 1 upon n into P2 raised to 1 minus 2n upon n. So we can cancel this n minus 1 upon n, both sides, that will be cancelled, okay. So we will be left with 1 upon P1 raised to n minus 1 upon n into P2 raised to minus 1 upon n equal to P3 raised to n minus 1 upon n into P2 raised to 1 minus 2n upon n. So P2 let us take on one side and other terms we can take on other side, okay. So it will be P2 raised to minus 1 upon n divided by P2 raised to 1 minus 2n upon n. This is equal to P3 raised to n minus 1 upon n into P1 raised to n minus 1 upon n. It is multiplied here. Okay. So this, if you calculate, if I take it on this numerator, its sign will be changed. Okay, so it will be let us say minus 1 upon n. So it will be plus 2n minus 1 upon n if I take it here. Okay. So this is equal to P2 raised to minus 1 upon n plus 2n minus 1 upon n. This is equal to P1 into P3 raised to n minus 1 upon n. So here you can see it is becoming P2 raised to 2n minus 2 upon n is equal to P1 into P3 raised to n minus 1 upon n. So I can write P2. If I take 2 common here, it is n minus 1 upon n. Here also it is P1 into P3 raised to n minus 1 upon n. So as this is common, so it will be cancelled. So we are getting P2 square equal to P1 into P3. Hence P2 is equal to under root of P1 into P3. So this is the condition for maximum efficiency or minimum work required in two-stage reciprocating air compressor with perfect intercooling. That means your intermediate pressure should be equal to the under root multiplication of pressure P1 and pressure P3. So